Before heading to the video, if you haven't subscribed the channel, do subscribe it and don't forget to click the bell icon for the latest update notification. If you like the video, do like, comment and share. Stay tuned with Learnbay.co. Happy learning!
Now there is one thing that we never touched, and although it was available in a lot of code actually, or it was mentioned, but we were not looking into that direction. So you might remember there is something, a word called regularization. What is regularization? So I might have told you, okay, so first remember, okay, does anyone remember what is L1 norm and L2 norm? We have talked about L1 and L2 a bit. Maybe under different names actually we have talked about, but we have definitely talked about it. And this is a Manhattan.
Yeah, the distance calculation.
It's a distance calculation, very well. So basically it is simple that whatever delta x, let's say if we are dealing in two variables, then this is Manhattan. And what is Euclidean?
X squared plus, yeah.
Make sense? Okay, just try to remember this because this will come in really handy understanding this topic. Okay, so I never showed you polynomial regression through sklearn, have I? Have you seen me doing a polynomial regression through sklearn? Again, you do understand not all the regressions can be actually be linear. So why we haven't done polynomial regression through sklearn?
If I remember, you had mentioned that sklearn is primarily when they are all linear.
Yeah, actually it doesn't have a function called polynomial regression. It has something only called linear regression. Okay. But I did tell you it is doable. You can do it. There is a very simple trick, which now, because now you understand the kernel trick, you will understand it immediately. This is why actually it should be taught with regression itself, you know. But people don't appreciate. Even I think some other instructors will teach you this topic with regression itself. But I don't personally appreciate it because people miss the essence why it is required. So let's say I come up with a simple regression line or a regression problem, which is very easy to solve, as you can see. So drawing a line here is not going to be very hard, is it? You can draw a regression line here easily. So if I were to run a linear regression, it should not be much of a problem.
Yeah.
Okay. So simple numerical regression we are talking. So again, I import the linear regression model. I do a fit intercept and then I fit the model and then I plot the outcomes. Okay. This makes sense? Any problem so far? Miss, regression should not give you any kind of problem right now. Okay, very good. So people understand this part. Very good. Now, what happens if you wanted to do a polynomial regression and you can get your slope and coefficient and everything? So how do I get a polynomial regression done here? So can anyone give me an idea that how can I get a polynomial regression using linear regression function itself?
Like kernel trick, you can
Yes,
change.
very good. Kernel trick. Kernel trick, or it is also in machine learning, it is also called something called as a basis function. It's nothing, you just multiply or you transform the data basically. Okay. So it is like converting your sheet into sine wave and then the line over there, or if you were to put a sine wave over there, or if you were to take, let's say, imagine this as a page which gets converted to a sine wave. So this is your new sine world where the page like lives like this. Okay. So even if you add a straight line here, this straight line. Okay. Now, based on okay, so if you were living on this page, this will look like a straight line, yes or no?
Yes.
Very good. But in our world, what it does looks like?
Sinusoidal curve.
Perfect. It looks like a sinusoidal curve. Okay, same trick we are going to use it. You can do it for regression classification, both of them. So it is called basically basis function. Idea is exactly the same. The trick is to adapt linear regression into a non-linear relationship is to transform the data. Or basically to come up with a polynomial regression, you will have to convert the data like this. Okay. How can I do this? How can I get this polynomial basis function in sklearn? Means I don't want to do a manual multiplication because I don't know about data much here. So I don't want to do a manual multiplication, plus it's complicated. So why would I go column by column anyways? So what is a better way of doing things here? Means this is the part we have already covered, like, but still I want to make sure that everyone is on the same page.
Multiply with the basis function.
No, but how do you get this basis function? Isn't that the trick? Come on, like you have already seen this actually. It's not something new right now. But let's just see that how many people get it immediately. How do I get this polynomial basis function in sklearn? Remember, not doing manual multiplication through sklearn itself. And you have seen this, that's the funny part.
By by looking at it from different angles, as in
What
projecting
is
it.
saying? No, we're just trying to convert into a higher order. There is no point of looking at stuff. We are not
When I say
doing.
looking means I'm saying projecting it into a different.
No,
So you
but look,
create.
after 3 dimensions, what you will do anyways? Like, understand, no?
Mm.
That idea doesn't really make sense after 3 dimensions. I'm simply saying I have to convert my data into a higher order function. Okay. What is the simplest way in sklearn to do that? Guys, it was in pre-processing techniques. How are you forgetting this one? Like I even have told you that this will come later. Polynomial features. Very well. Very good, Samadhi. What was polynomial features? Anyone remembers? Anyone? Come on, like this has been discussed already. So if I have an array 2, 3, 4, 5, 6. So what does polynomial features where power is 4 and okay, include bias is nothing, it is just to put an extra bias over there. Is false. Okay. So what is really this 4 basically? Can anyone explain me? It's a degree, right? Yes, some people have answered it correctly. So order or it's a degree. So when I run this, how does the processing works? I have already explained this, so I will really appreciate if you guys can also help me out. So this is what? Imagine this is X, okay? X anyways. So what is this first line? First column is what? This column is x to the power 1. This column is
2, 3, 4.
very good. Now, if you look at, if I provide this data to my linear regression, what does it estimates for? Think about it. If I provide this data to my linear regression, then what it is really trying to do? Y is equal to, think about it again, theta 1, x1. Now this is power 1, theta 2, x2 squared, sorry, x1 already, theta 3, x1 cube, theta 4, x1 to the power 4. Maybe there is a theta naught, there might not be theta naught. So if in case the equation is y is equal to 5x squared, what will happen here? Once the regression runs successfully, let's say, what will really happen?
everything other than theta 2 will become 0.
Yeah, very good. That is the correct assumption. Basically, here, maybe this will go very close to 5, and rest of them should ideally become 0. Okay, maybe theta naught is not, or maybe even this is 0. So see, you are able to approximate a polynomial function.
Yeah.
This is how you run a polynomial regression. Basically, it has to be done in 2 steps. First, you convert your data into higher order through polynomial features, and then you run your simple linear regression. Okay, so you make a pipeline. See here, we make a pipeline. It's a very simple thing. So this pipeline is a perfect representation of a polynomial regression. Can you see that? So even if the data is of higher order, see, we are able to get a very good fit. You can see this data set is definitely not linear, right? I can show you it is very much a sine curve basically. But order of 7 is also able to kind of reproduce or approximate it very well. Make sense? And if you want to understand the total equation, I can help you with this, like, so we can get with the, but I don't think so I have the model fit or what. So of course it will come on steps 1. So once after you have run the training, you will find this is a linear regression itself. Maybe I can also do something like this, linear steps, and
So one question, one year
yeah,
then.
yeah, please, please, please. Let me just see if I can get the coefficients here. Okay, so tuple has nothing called coefficient. Okay, no problem. Yeah, yeah, please go ahead. What was the question?
So if you go back to the previous that thing theta 1 theta, yeah, where you had the multiple
This one?
yeah, this one here. So for x1 we are assuming, let's say theta 1, then theta 2 for x square, theta 3 for x cube, and theta 4 for x4, let's say, okay, each of these
Right, right.
problems. Now the data is 2 3 4 5 6 as one set of data. So wouldn't theta 1 itself be as in within the theta 1, I understand theta 1 x1 and theta 2 x2, but that x1, the dependability of the target on this feature again will be some alpha 1 2 plus alpha 2 3 plus alpha 3 4 alpha 4 5 alpha 4 6, am I right? What I
Mm,
mean is,
no, but x1 is a one column only. So why are you thinking it as in terms of different columns?
because I'm thinking in terms of that it has got it is poly. So poly meaning that the feature which is there. Uh, okay.
But again, x1 is just one column. So even if you have poly, what you want is, we basically want 4 columns just in case. Okay, just to understand which order it works the very best. Sorry, x1, all the time x1 here. So you have recreated your data, same data, into four columns, and you have put squares. And let's say you put theta 1, theta 2, theta 3, theta 4. Okay, and you come up with the equation. The idea is, while doing the correct regression, correct order power will be highlighted more and rest of them will be suppressed.
Okay. Might be I'm overthinking it. Okay, fine.
Now, do you understand? X1 is just one feature. We are not talking about multiple features, first of all. The only thing which we are talking is, can I create, wait. So look, you do not know what is the order beforehand, and after 3 dimensions, it's not possible to plot. Let's say you have X1. So you think, why don't I stress test with X1 square, sorry, X1 cube and X1 to the power 4. And basically put theta 1 here, theta 2 here, theta 3 here, and theta 4 here. Okay, and plus, plus, plus. And imagine this as a, maybe if you want to put logistic, or if it is numerical, then it's directly numerical.
Okay. Yeah, so let me take a quick example. Let's say my salary is dependent upon my age, number of years in the company. Okay.
But
And
go ahead.
and might be my education, but education will be more of a discrete thing. So I don't know.
Yeah, you can't use discrete. Again, in numerical regression, it all has to be numerical. You can take some kind of performance score in between 0 to 10 if you
Yeah,
want to.
yeah, good points. Let's say my performance. So there are three parameters, three features which are there: age, a number of years in the company, and my performance rating, which is there for last year. Let's say. Now, X1 is age, X2 is number of years, X3 is my performance. So X1, then X1 square is nothing but my age, then age square, then age cube, then age 4.
Yeah.
So even if I get theta 1, theta 2, theta, that's just my salary. I have to get a Y, which is theta 1 of age plus theta 2 of number of years in company, and theta 3 of my rating. So I'm only estimating then theta 1, theta 2 in this model, X1, X2 square, only for the dependence of the age, let's say.
Okay. Let me take this, simplify this for you. Okay. So maybe I will just take two things. Okay. And just to, and the Y is salary. Okay. This is sal, and this is your score. So let's say you get an annual score or something like that. And this is your numbers of years of experience. Okay. So let's make everything numerical. Yeah. Now, we don't know that it is directly a linear relationship, yes or no. Of course, you can through mutual info, or maybe through even correlation, you can get some ideas. So imagine this is X1 and this is X2 and there is Y. Agree?
Yeah.
Okay, so the equation is something like this. Now, the problem is, if it is a polynomial regression, I do not know the power. So ideally what we do is theta 1, X1, linear regression takes these assumptions.
Yeah.
And there might be a theta naught. There might be.
Yeah.
This is the assumption it takes. So fundamentally, it's a plane. You agree with this?
Yeah.
Okay, very good. So now the problem is, and this is the part you have to think very carefully. There's no guarantee X1 and X2 are directly linearly related with the outcome, are they?
Absolutely. And okay. Yeah.
So maybe while doing the transformation, just take a power of 2. Let's not make it really complicated. So if I were to take a polynomial order of power of 2, does anyone remembers what are the columns? So the first one is the bias. So basically everything will basically be 1, 1, 1, 1 itself anyways. This one will be X1, this will be X2. Agree?
Yeah.
What is the next one?
Yeah.
What is the next one?
X2 square.
No.
Oh, okay. That way, multiplication wise, yeah. Okay.
This also will be there. So when we will play it out, okay, we can imagine this as X0. When we will play it out, how will this polynomial regression thing will work?
So then it will be theta 1 of X naught, sorry, X naught anyway. Yeah, so some theta naught of X naught, theta 1 of X1, theta 2 of
You're going in the correct direction. Let me help you out with this one. Okay, so first I will have to make an assumption that your Y is nothing but some theta 1 of X1. So X1 is of first order power, but it is correlated or is related with X2 somehow in a squared order. Okay. So if the working happens correctly, if the linear regression works correctly, what will happen? And so we will take something like this kind of equation. So we will take theta naught X naught plus theta 1 X1 to the power 1, theta 2 X to the power 1. The next one is theta 3 X1 to the power 2, theta 4
X1, X2.
Very good. And theta 5. Okay. Again, it's a trick of regression itself. If I were to just reduce, think about this carefully. All of these to be 0 most of the times. This becomes 0. This becomes 0. And this becomes 0. This also becomes 0. This remains as it is, or whatever some value it takes. So doesn't the whole equation actually just became, which is very similar to this equation?
Got it. So this right, the blue thing which you wrote on the right, which is there, the full expansion, that clarifies what I was saying. So if I take all the X1s together, then it is theta 1 of X1 square plus theta, let's say there was another thing, the theta 1 of some theta 3 of x1 cube. So all the x1 can be clubbed together, and that's what I was coming to. I got my answer. I got my answer.
Very well. Does anyone has any problem with it? It looks confusing, but once you understand, it's like a pretty beautiful idea that rather than manually doing it, why don't just we provide a power, let it take all the combinations, all the powers, and let it regress. It will try to find the best ones anyways. Okay. But now it comes with its own problem set. Can anyone think about the problem? In this approach, what is the problem?
Overfitting.
Overfitting. Why?
Because it will go to that nook and
Because we
corner
don't,
of each and every
yeah,
curve.
no, but because we don't know how much power is required to
Okay.
get, because again, after 3 dimensions, you will not be able to plot anything, right? So you will be dependent on what to understand what is your regression model doing? Your score values, right?
Yeah.
Your R2 score or your MSE, you will keep looking at it. But that doesn't tell you it is overfitting or not. Again, even if it is overfitting in training data, it will actually give you a really high value. So my point is, okay, so I think I have given you the mathematical idea anyways. What happens when I increase the power? Come on, anyone? What happens when I increase the power of a function?
Number of carbs will increase.
Exactly. It becomes mathematically complicated, or graphically, if you want to look. If you put more number of powers, the curve will start to bend a bit more. It means it will try to bend too much, and that is a classical case of overfitting. Now the problem is, how do you know what is the optimal power? Maybe I have tried and tested this 7 a lot of times, but how do you know where to stop? Which, if you were to run a grid search, it would be tricky. A lot of different amount of powers can give you very similar results. So which power, ideally, again, remember Occam's razor, whenever in confusion, you go with the simplest one. This is the whole problem when you put the power over there. Sometime it can go out of steps, or wait. Okay. So let's say this is the linear regression. So let's say, what if I take power of 29? What is to stop me here? So what will be the problem look like? In some areas it is not fitting at all, and in some areas it is overcompensating. Can you see that?
But I thought, sir, if you increase the power, it will only try and fit in everything. So there should not be missing. It should be not compensating. It will be overfitting. But does it really miss the left-hand side?
It can happen. It can. Both things are totally possible. It depends again. It depends how the optimization has been done internally. So if your thetas are not been correctly estimated, maybe based on complexity or the loss function, you could get a scenario like this. So it is possible.
Okay.
And sometimes we might have to increase it really too much. And you will see as you keep increasing the power, because the equations are becoming more complex now, you will see it might start to miss completely, but then you will see a very specific pattern. It is whatever it can, it is trying to go through each and every point. Okay. So here it is an easier example. In sine curve, it is slightly tricky actually to do that. So in sine curve, it is hard to fool. But if it was some normal order power, you would have seen the problem. That it is really easy to kind of, how do I say, basically overfit in these scenarios. So again, here we are taking, let's say 29, 27, or maybe just let's take 23. And you start to see the issue, basically that maybe it misses something in because of the sine curve periodicity problem. Okay. But wherever you see this issue, and you can see this, right? It starts to go through point by point, and it starts to make bends to adjust to each point, which is classic case of overfitting. So how do we stop, or how do we avoid the problem of overfitting? although there are different ways, and of course hyperparameter is one of them. The first thing is called, or basically it is referred in regression as ridge regression or lasso regression. Fundamentally the idea is same. It's a regularization or it's a penalty. Basically we put a penalty over there to balance it out. Now what is penalty exactly? In plain English, what does penalty means?
We're paying for something we have done wrong.
Exactly. So basically what I will do is I will change your loss, or I will alter your loss function itself. So what ideally your MSC is like this, or maybe 2m, and summation y hat minus y square, right? This is your loss function, agree? But what if I put a new term now altogether, and all the thetas, basically theta I squared, or maybe I think it should be 1 by, okay, I can do like something like this. Okay, this is the penalty term. So what penalty term is doing is it is pushing it out of any kind of, so many times optimizations can also be thought as, in this hill surface, basically it has gotten stuck somewhere. Maybe it is the global minima, maybe it's some local minima. So what does penalty term does is it kind of moves the target around. So it gives us enough variability to basically not get stuck somewhere. Basically, a lot of time overfitting is thought like as being getting stuck in a ditch and thinking this is the end of the discussion or this is the best I can do. By pushing it around through the penalty term or kind of giving it a more loss value. So basically putting it like, okay, think about it. If you were here, let's say for some reason, okay, if you were really here, if I were to add or subtract some extra term, what will really happen? If you are here right now, and if I were to add some penalty term, add or subtract, doesn't matter, what will really happen?
We will move forward or backward.
Yeah, either you will be here or you will be here. Okay. Now, depending on, again, on your optimization, it depends, you might go in some other direction altogether. So the idea is it doesn't just get into completely get into a ditch or something like this. And it creates enough variability or enough problems for the optimizer to again reassess the scenario. So whenever it gets something wrong or if it falls far apart, it changes or it penalizes it. So basically what happens is when you penalize it, it tries to make corrections very fast. Okay, or again try to correct the optimization. And the hope is in long run, it is able to correct itself. So the basic idea of, so again, remember whatever we are showing now here, unfortunately, the equation that I have copied is in terms of alpha, but because alpha is also the step value or learning rate, ideally one should think it as lambda. Okay, in a lot of mathematical books, it is lambda itself. Okay, and it is of second order. So summation of all the theta values. Okay, so it is basically by the penalizing by the sum of squares of the model coefficients. Okay, and you can think this as alpha because unfortunately it is also written as alpha in the parameter setting. But in a lot of books, it is referred as lambda itself. It's a free parameter which controls the strength of penalty. So if you were to increase this parameter, the penalty strength will be really high. Ideally, we do not go beyond 1. Okay. So this is called L2 regularization, and it is imported in regression models by Ridge. Okay. So when you run ridge regression, so by default, it means it is running the linear regression with L2 regression, L2 regularization. Now, if you remember in your logistic and in few of them, I might have told you that there is something called L1, L2, but I told you to ignore at that point. Remember the penalty term? Now, I hope you will understand what these penalty terms really are. So fundamentally, again, you can utilize them in any other coefficient based model, and logistic regression is definitely one of them. And this is what the whole idea is. So when we talk about ridge regression, what ridge regression is very simple, is basically linear regression plus L2 regularization. Does this make sense? What is ridge regression? So just to compare, polynomial order of 23 and then your linear regression was looking how? Like this. Can you see this?
Yeah.
Okay, very well. Now, once I run the ridge regression, which just contains L2 regularization internally, what happens? You get something like this. Do you see an improvement? A bit of, definitely. I'm not saying it is amazing or something, but do you see a bit of improvement with the compared to the previous graph?
Yeah.
Yeah. So the extreme curves where it was really trying to fit to each point, it has let go of that tendency. And it has been brought to a more simplified or generalized thing. So it is more of a generalized model than more of a overfitting model. And this is what ridge regression or achieves. So this is what L2 regression can achieve. And similarly, there is something called lasso regression, which is just L1 regression. Same idea. If you look carefully, it is directly the summation of theta and absolute values, of course, and alpha value, which is again a free parameter. Now, the problem is because of geometric reasons, actually it prefers or it is more used in sparse models. So like in NLP data where most of the data is basically 80 or 90-95% data is almost sparse, which basically it is zero. So in those cases, L1 regression actually does better. And you will see it here that in this case, lasso regression actually doesn't tends to do that well because these are your like dense models. So it like oversimplifies. That's the whole problem. Then it starts to oversimplify at some point, which might not also work very well. Okay, so again, it has to be experimented with.
One
But
question.
in mostly in dense models, we mostly prefer L2 regulation, and in sparse regulation, we prefer L1 regulation. Or sparse models, we prefer L1 regulation. You were saying something?
Yes, sir. What I was saying was, when you're taking 23 and 29 as polynomial features, that is more for showing it to us, or that is generally the way? Because my thinking would be instead of first going for lasso and ridge, might be if we reduce polynomial to 5 or 10 and the
Yeah,
fit.
yeah. No, no, I'm not saying that that is not to be done. Okay.
Ah,
I
okay.
just simply, okay, this was to showcase you the impact of regulation. I'm
Got
not
it.
saying that all of a sudden just do regulation, forget about the hyperparameter tuning. No, no, no. That was definitely not it. Some days, even after doing, because again, the models can become really complex, right? So it is not easy to visualize these things. So you do not know after 3 dimensions, you will not be able to know, or it is means there are few metrics, but it is very hard to know which one is causing more impact after a while.
Got it.
Is
Got
it
it.
the data cleaning which has caused more impact? Is it the hyperparameter tuning? Or is it some kind of regulation that I put? So we basically take an assumption we have to do all of this to get the best version of the model. Does that make sense?
Got it. Got it. Well, look, where I was thinking was like what you said, Occam's razor might be the simplest
No,
model.
I totally get it. Basically, yeah, you might be thinking that why wouldn't I experiment with grid search than doing all this drama in life, right? You're totally right about this. And of course, maybe experiment with thing grid search would have given you the better result immediately. But just to explain you that some days you will get stuck with overfitting. It will just happen.
Yeah.
So
Okay.
wherever you have a parametric model, wherever you have these theta terms, like in logistic regression and linear regression, you can run something called regularization. And that can also kind of affect or cut out the impact of the overfitting. And these pictures are just to represent how or what they are able to achieve.
Got it. Got it.
Make sense?
Yeah. Yeah. Sure.
Of course, basically, and this is the final takeaway I want you to have, that basically we have covered all of this already. Just to take a very generalized idea. When you are clearing or when you are trying to understand or okay, so now while we are almost at the end, basically I want to tell you that look, what is required. Okay, first you need to have a good understanding of data itself. So there are some domain knowledge problems. Okay, that there could be hidden confounding variables, and that is very hard to figure out through statistical relationship. So you can do your normal EDA stuff to get the understanding of data, right? Then proper pre-processing and cleanup of data is required. Okay. Then applying correct models. Okay. Now it is not that easy. It definitely comes with practice. So it will be a lot of hit and trial first of all. Fourth step, applying regularization wherever possible. I'm not saying it is always available, when possible. Okay. Tune the hyperparameters. So you tune your hyperparameters to get the best model, and then you will have to do either grids. So this will be done best through the grid search, and then cross validate your result. Else repeat. Okay. So remember these basically 6 major steps according to me, that these 6 steps as in normal machine learning, and of course there could be a 7th step as well, which is good visualizations. Wherever possible, I'm not saying it is always available. So while you are doing your data science, you have to think about total of these 7 steps, and the 6 steps are definitely a bit of in a cyclic way. It is not like, this is why like sometimes teaching like one topic is very hard, because again it is connected with something else as well. So all of these things go hand in hand, and you have to develop a complete understanding to go forward with it. Does this make sense? Like this is like the fundamental idea that I want you to have, that how to proceed in terms of data science.
So the regularization application will be a part of choosing the correct model, am I right? It will be like
Or applying, or is like yeah, you can say that, but again I have separated it because first of all it is not actually applicable in all the models. Okay.
okay,
It only works when you have like some parametric model like in decision trees. There's no concept of regression.
got it.
Now remember guys, if you were to look into machine learning literature extensively, combining supervised unsupervised examples, there could be more than 300 algorithms. Like I was reading that there was one survey paper which concluded there are 153 clustering methods only. So it is almost sorry, it is almost impossible to teach you all or anyone. Even I do not know more than like 10% of these algorithms, to be very honest. I only read whichever is of my interest area or research area, and I understand the basics fundamentally. Okay. And based on that, I extrapolate what this algorithm might be doing. So it is almost impossible to teach you all the algorithms. Even if we did it, people tend to forget. Earlier, we had this policy, we would cover 5, 6 more algorithms, but people will not be able to handle it anyway. So the idea is you go ahead with the basic algorithm first. And then as the requirement comes, you go ahead and start dealing with more complex algorithms. We are actually thinking to break the machine learning in 2 parts now. One is normal machine learning, the basics, and the advanced machine learning, where we can teach advanced machine learning with some more better, not better, like more complex models actually as required. Okay, so that hopefully will happen in future really soon. As I've told Krishna last year as well that these we need to teach a bit more algorithms, like few boosting algorithms and everything. And he told me like they are designing another course which will be called advanced machine learning, where we can teach boosting and some other algorithms. But so far that has not been put in practice as I know. So hopefully that happens really soon, and maybe we can teach some more algorithms related to machine